Welcome to the Deep Dive. You're here because you want to quickly get a handle on something complex, right? Today we're plunging into the world of dental casting alloys. We've got some videos, some PDF excerpts as our starting point.
Yeah.
And our goal is pretty simple. Give you a clear understanding of these essential materials without, getting totally lost in the technical weeds.
Exactly. Think of this as your shortcut, really. Your fast track to grasping the materials that, well, they underpin so much of modern dentistry.
Yeah.
We'll look at what dental alloys actually are, the different ways they're classified,
Yeah.
the crucial properties they absolutely must have,
Right.
and how they're used in everything from, say, crowns to the frameworks for partial dentures. By the time we're done, you should have a really solid grasp, feel genuinely informed.
Okay, let's dive in then. Unpack this.
Yeah.
What exactly is a dental alloy?
Okay, so at its core, dental alloy is basically a blend, a mixture of more than one metal. And it's not just, throwing metals together randomly. It's a precise combination designed to achieve specific advantages for use inside the mouth.
Okay, like what kind of advantages?
Well, think about those porcelain fused to metal crowns, PFMs, or the structures and bridges, the frameworks for removable partials. They all rely on these carefully engineered metallic mixtures, the main aim. Create something that's biocompatible so it won't harm your mouth tissues.
That's cool.
And strong enough to handle the daily stresses, chewing, biting, all that.
So definitely not just chucking some metals in a pot. There's real science here.
Oh, absolutely.
Yeah.
And one of the first big distinctions you make is between noble metals and base metals.
Noble metals like golds.
Exactly. Gold, palladium, platinum are the big ones. But there are others too. Rhodium, ruthenium, iridium, osmium. They share similar valuable properties.
And what makes them so valuable?
Well, they're really good at resisting corrosion and tarnish, which is obviously vital in a moist environment like the mouth.
Makes sense.
Plus, they're generally very biocompatible, and they tend to have good malleability and ductility, meaning you can shape them pretty easily without them breaking.
Sounds perfect. So why aren't all dental things made of pure gold then?
Well, a few reasons. First, noble metals are often quite dense, heavy,
Okay.
and maybe, obviously, they can be expensive, really expensive sometimes.
Right.
And while they are generally well tolerated, some people can still have allergic reactions. And here's a really key point. For some things, like those PFMs we mentioned,
Yeah.
we actually need base metals mixed in.
Hang on. Why add the lesser metals if the noble ones are so good?
Because base metals are much better at forming a chemical bond with porcelain. Noble metals, well, they're noble because they're kind of inert, chemically speaking. They don't readily react.
Okay.
So for that really strong, lasting connection between the metal base and the porcelain on top,
Yep.
base metals are essential players.
Right. It's about getting the right properties for the specific job, not just using the shiniest metal.
Precisely. Tailoring the material.
Now, the material mentions alloys are classified in a couple of ways. Let's start with the one based on noble metal content. That seems pretty fundamental.
It is. It's a common way to categorize them, and yeah, important. You generally see three main classes: high noble, noble, and predominantly base metal.
High noble. HN. What does that entail?
Okay, so for an alloy to be called high noble, it needs at least 40% gold by weight.
40%. Okay.
And a total noble metal content, so gold plus palladium, platinum, etc., of at least 60% by weight.
Got it. So mostly noble, with a significant chunk being gold. What about just noble then? N.
For the noble category, an alloy just needs to have at least 25% by weight of noble metal elements in total.
So no specific gold requirement there.
Correct. Just 25% or more noble metals combined.
And the last one, predominantly base metal, PB. Seems pretty obvious.
It is, yeah. If the alloy has less than 25% noble metals by weight, it's in this category.
And why is this classification so important? You mentioned exams.
Well, partly that, yes. But more practically, it gives you a quick general idea about the alloy's likely performance in the mouth, especially its resistance to corrosion and its biocompatibility.
So higher noble content generally means like better corrosion resistance.
Generally speaking, yes. That's the trend.
Okay. Now the other classification, based on mechanical properties. This sounds more about strength and flexibility.
Exactly. Both the ADA, the American Dental Association, and ISO, the international standards body, they classify alloys based on yield strength and percent elongation.
Yield strength.
Yeah.
That's how much force before it bends permanently.
Precisely. And percent elongation tells you how much it can stretch before breaking. That's a measure of its ductility.
And these are types 1 through 4.
Yep, types 1 to 4. Representing a spectrum, really, from lower strength and more ductility to very high strength.
Okay, walk us through them. Type 1.
Type 1 alloys have low yield strength. They're mainly used for things like inlays.
Inlays, like fillings, but solid?
Kind of, yeah. Prefabricated, often ceramic or gold. They need some strength, but nothing extreme.
Gotcha. Type 2.
Medium yield strength, still used for inlays, but also onlays.
Onlays cover more of the tooth, right? Like the cusps.
Exactly. They cover one or more of those pointed cusps, so they need to handle a bit more biting force. But also thin cast backings for crowns, pontics.
Pontics are the fake teeth in a bridge.
The very ones, yes. Also full crowns, and even saddles the base part of a removable partial denture that sits on the gums.
Okay, getting into more heavy-duty uses, which leaves type 4.
Type 4 is extra high yield strength. This is the really tough stuff.
Like for what?
Saddles again, bars, clasps of bits that hold a removable partial denture in.
Ah, the clips.
Exactly. Also crowns, bridges, and the entire framework for some removable partials. They need to be super strong, really resistant to bending.
Okay, here's something interesting the material mentioned.
Yeah.
An inverse relationship between noble metal content and yield strength. How does that work?
Yes. That's a really crucial point. Generally, and this is a generalization, but it holds true often, as you decrease the amount of noble metals,
Yep.
the yield strength tends to increase.
So less gold means stronger. Seems counterintuitive.
Well, think about it. Noble metals are known for being ductile, malleable, easy to work with, right? Those properties don't always mean high strength. Base metals, on the other hand, often contribute more to hardness and strength.
Ah, I see.
So while your high noble alloys are fantastic for corrosion resistance and biocompatibility,
Yeah, right.
your predominantly base metal alloys are often picked when you absolutely need high strength above all else, but it's a trade-off.
How so?
More strength often means less ductility, less malleability, harder to adjust, maybe more brittle in some ways. So, for a back molar needing pure strength, maybe a base metal alloy is fine. For a front tooth crown, you might lean towards high noble for looks and biocompatibility, and design the crown differently to compensate for slightly lower strength. It's all about balancing the needs.
Fascinating balance.
Yeah.
Okay, let's move on to the desirable properties list. We've hit biocompatibility and corrosion resistance. What else makes a good dental alloy?
Well, thermal properties are huge, really critical.
Thermal, like how it handles heat.
Exactly. Two key things: melting range and thermal expansion. The melting range needs to be low enough for casting.
No, it flows easily into the mold.
Right. It needs to flow smoothly, capture all the fine details of the mold, which is usually made using a wax pattern, the lost wax technique. Without being so hot, it damages the mold itself, the investment material.
Okay, practical casting stuff. What about thermal expansion?
This is super important, especially for those PFMs, the porcelain fused to metal ones.
Why specifically for them?
Because the metal and the porcelain have to expand and contract at very similar rates when the temperature changes.
Like when you drink hot coffee, then ice water.
Precisely. If the metal expands way more than the porcelain, or contracts much faster, crack. The porcelain can chip, crack, or even just pop right off the metal.
Yeah.
Debonding.
Yikes. Okay, so they need to be thermally compatible. That's critical for long-term success.
Absolutely crucial. You want that restoration to last.
What about strength? We talked yield strength with the types. Anything else?
Stiffness is another big one, also called elastic modulus.
Stiffness. Why is that important?
Especially for bigger things. Long bridges, the connectors and partial dentures. High stiffness prevents the framework from flexing too much under chewing forces.
Right, you don't want your bridge bending.
Exactly. That could lead to failure or just be really uncomfortable.
Yeah.
And yeah, while compressive strength resisting squashing is usually pretty good in most alloys, we focus on yield strength because that's the point where it starts to deform permanently in the mouth.
Okay, stiffness for stability. Got it. What about actually making the restorations? Fabrication properties.
Yeah, several things matter there. We mentioned flow for casting. That relates to flow and wetting. The molten alloy needs to flow well, obviously, but also wet the mold surface.
Wet the surface, like spread out evenly.
Yeah, have good contact, no bubbles or gaps, accurately replicate the shape. Then there's hardness.
Hardness. Used to be hard, right?
Well, yes and no. It's a balance. Hard enough to resist wear in the mouth,
Okay.
but not so hard that the dental tech can't finish and polish it smoothly. A rough surface is bad for gums, bad for hygiene.
The Goldilocks zone for hardness. Robust but workable.
You got it. Finding that sweet spot.
Okay, and we touched on this, but let's circle back to porcelain bonding for PFMs. You said base metals help.
Yes, it's all about forming a thin, stable oxide layer on the metal surface.
An oxide layer, like rust.
Sort of, but controlled. This oxide layer is the chemical bridge. It's what the porcelain actually bonds to.
I see.
And noble metals, being inert, don't form these oxides easily. That's why pure gold isn't ideal for TFMs. You need those little bits of base metal, iron, indium, tin, stuff like that, added to promote that crucial oxide layer.
Fascinating. And the color matters, too.
It does. You ideally want light-colored oxides. Dark oxides can sometimes show through the porcelain, especially if it's a lighter shade, and affect the final look.
Wow. Even the invisible oxide layer impacts the aesthetics. Amazing.
Yeah.
And finally, the elephant in the room, cost.
Yep. Can't ignore economics, especially with precious metals like gold involved.
Labs have budgets.
They certainly do. They have to balance the ideal properties with what's affordable. That's partly why you see palladium used quite a bit.
As a cheaper, noble alternative.
Exactly. It's still a noble metal, offers good corrosion resistance, but it's generally less expensive than gold, so it helps manage costs while still providing many benefits.
Makes total sense. Okay, let's drill down specifically into those PFM alloys now. Metal ceramic processes. We know oxide formation is key for bonding.
Right. Those small amounts of base metals, iron, indium, tin, get added to noble or high noble alloys, specifically for PFMs. When the metal is heated before applying the porcelain, these elements migrate to the surface and form that necessary oxide layer.
Okay.
And the porcelain then chemically bonds to that layer during the firing process in the dental oven. But it's not just about any oxide layer. No, it has to adhere well to the metal itself. If the oxide layer is weak or kind of flakes off, the porcelain will just peel away with it. That's delamination.
So a strong, adherent oxide.
Got it.
Got it. And the thermal contraction thing, we know they need to match. But you mentioned something about residual compressive stresses.
Ah, yes. This is quite clever, actually. Ideally, you want the metal to contract just slightly more than the porcelain when it cools down after firing.
Slightly more. Why?
Because that puts the porcelain layer into a state of slight compression.
Compression. Squeezing it.
Exactly. And porcelain, like most ceramics, is much stronger under compression than it is under tension being pulled apart.
Ah, so that slight squeeze makes the porcelain tougher, more resistant to cracking.
Precisely. It enhances its fracture resistance. It's a way of engineering strength into the system. But again, the key is slight. Too much mismatch, even in this direction, causes problems.
A delicate balancing act. Very cool. What about the metal's melting point? Solidus temperature, was it?
Yes, solidus temperature. That's the temperature where the alloy becomes completely solid. This needs to be significantly higher than the temperature used to sinter the porcelain.
Sintering. That's baking the porcelain powder.
Essentially, yes.
Yeah.
Fusing the powder particles together into a solid mass. If the metal solidus temp is too low, the metal framework could actually start to soften and sag under its own weight during that porcelain firing cycle.
Oh, wow. Like the foundation giving way.
Pretty much. And that leads to distorted frameworks, open margins where the crown meets the tooth. Basically, a failed restoration before it even gets to the patient. The metal has to stay rigid while the porcelain is being baked onto it.
Makes perfect sense. Now, a lot of PFMs use predominantly base metal alloys, right?
Mm-hmm.
What are the key things to know about working with those?
They often require higher melting and casting temperatures than noble alloys.
So, different equipment needed.
Often, yes. You might need acetylene oxygen torches instead of just gas air, or electrical induction heating units.
Yeah.
And the investment mold material needs to handle that extra heat. Phosphate or silicate bonded investments are common.
Higher temps, tougher materials.
Mm-hmm.
What about handling them in the lab? Castability? Hardness?
Well, some base metals, especially those with a bit of beryllium added.
Beryllium?
Yeah, it improves flow, makes casting easier. But beryllium is a health hazard, so labs need strict controls when using those alloys.
Okay, good to know.
Generally, base metal alloys are quite hard, which is great for wear resistance in the mouth, but it makes them harder to grind, adjust, and polish smoothly. It takes more effort. Common types for PFMs are nickel chromium and cobalt chromium.
And they have good strength properties.
Yes. Generally, a higher elastic modulus, they're stiffer than noble alloys.
Which means you can make the metal part thinner?
Often, yes. You can design thinner copings and connectors while still having enough strength. And they usually have good fatigue resistance, too. They hold up well to repeated chewing forces over time.
So stiffer, potentially thinner, good fatigue life. Sounds good. but potential downsides too, incompatibility.
The big one is if the thermal contraction is mismatched the other way. If the porcelain contracts more than the metal as it cools.
Instead of compression, you get
Tension, tensile stress, pulling forces within the porcelain, and porcelain is weak under tension.
And so it cracks.
It can lead to cracking or the porcelain pulling away from the metal debonding again, so getting that thermal compatibility right is just non-negotiable.
Absolutely critical. What are some common reasons PFMs might fail prematurely, like in the lab or shortly after placement?
Well, that thermal incompatibility is a big one. Poor framework design too thin where it needs strength, or maybe too bulky, causing stress. Improper metal surface prep before the porcelain goes on. If it's contaminated or not oxidized correctly, the bond fails.
Okay.
Errors applying the porcelain itself, trapping air bubbles, not condensing the powder properly, creates weak spots. And of course, problems during the firing cycles, wrong temperature, wrong timing, lots of steps where things can go wrong.
Sounds like it demands real precision at every stage.
Yeah.
One last PFM thing. Greening. What's that?
Greening. Yeah, that's a specific type of discoloration you sometimes see in the porcelain, usually lighter shades.
Turns green. Why?
It's usually caused by silver in the alloy. During the high-temperature firing, silver ions can migrate into the porcelain and cause that greenish tint.
Not ideal for a front tooth.
Definitely not. The solution is pretty simple, though. Use silver-free alloys for aesthetic cases.
Gotcha. Okay, let's switch gears. Removable partial dentures. RPDs. What's their basic job?
RPDs replace missing teeth when someone still has some natural teeth left. They get support from both the remaining teeth and the gums, the soft tissues.
And they have metal parts, right? It's not just pink plastic and white teeth.
Oh, yeah. The metal framework is the skeleton. It includes connectors, major ones linking sides, minor ones linking components, rests, which sit on the natural teeth for support.
Like little shells?
Kinda, yeah. Clasps, which are the clips that hug the teeth for retention.
Hold it in place.
Exactly. And mesh bases, which are like grids that the pink acrylic and the artificial teeth attach to.
Quite complex. So what do the alloys used for these frameworks need to be able to do?
Well, strength and stiffness, high elastic modulus, and yield strength are vital for the main body, the connectors, and rests. They can't bend or deform,
Right.
but the clasps need some flexibility. They need ductility so the dentist can adjust them slightly for a good fit without them snapping.
So strong and flexible in different parts.
Precisely. And of course, corrosion resistance is essential in the mouth. Biocompatibility too, no allergic reactions.
You mentioned allergies before.
Yeah.
Even to gold.
It's less common, but yes, some people are allergic to gold. More commonly, you worry about nickel allergies with some base metal alloys used in RPDs.
Nickel's a common one.
Yeah.
So what alloys are typically used for RPDs?
Cobalt chromium, or Cocri, is very common. It's strong, hard, wear-resistant, but it has a high melting point, needs special handling, and its hardness makes adjustments tricky.
Okay.
What else? Nickel chromium, NiCr, sometimes with beryllium added for better casting, though again, beryllium safety is a concern. NiCr casts well, it's strong and stiff, but the nickel allergy potential is the main drawback.
Right. So cochramium if nickel is an issue.
Often, yes. Then there's titanium in its alloys.
Titanium, like for implants.
Same element, yeah. For RPDs, it's lighter than Cocri or NiCr. It's very biocompatible. But it has a super high melting point, needs special casting, forms a reactive layer you have to remove.
Sounds tricky.
It is. And it's less stiff than Cocri, which isn't always ideal for a framework. It is more ductile, so clasp adjustment is easier. But overall, it's less common for full frameworks than Cocri or NiCr because of the processing difficulties and lower stiffness.
Okay. So mostly Cocri and NiCr, watching out for allergies. Why not use those high noble alloys? They sound great otherwise.
Two big reasons. Density and cost.
Density.
Yeah, high noble alloys are heavy. An RPD framework made of gold alloy would feel really heavy in the mouth, especially an upper one. Not comfortable.
I see. And cost.
Making a large, intricate RPD framework out of gold alloys would be incredibly expensive, just not practical for most situations compared to base metals.
Heavy and costly. Bad combo for RPDs. Got it.
Yeah.
Okay, last big topic. Metal joining. Soldering and brazing. Why is this important?
It's absolutely essential. It's how you connect different metal parts together, joining crowns to make a bridge, attaching clasps to an RPD framework, lots of applications.
Basically dental welding.
Or gluing with molten metal, yeah. And accuracy is critical. A bad joint means the whole thing can fail.
Okay, and the difference is temperature, right? soldering versus brazing.
Exactly. Soldering uses a filler metal that melts below 450 degrees Celsius. Brazing uses one that melts above 450 C.
So brazing is the higher temperature process. What do you need for these?
You need the parts you're joining the substrate metals. You need the filler metal, the solder or brazing alloy, which has a lower melting point than the substrates.
So you don't melt the main parts.
Crucial point, yes. You need flux.
Flux, what's that do?
It's a chemical agent, cleans the metal, prevents oxides from forming while heating, and helps the filler metal flow properly.
Okay.
And you need a heat source. Could be a torch for small jobs or a furnace for bigger ones.
Let's talk about flux more. You said it cleans and protects. Are there different kinds?
Yes, generally 3 types based on function. Surface protection flux goes on before heating. Think of it like a shield against oxygen. Boric acid, borax for noble metals, that kind of thing.
Okay, shield first.
Then, reducing agent flux. Applied during heating. If some oxides do form, this stuff chemically reduces them, cleans them off. Often contains fluorides, especially for base metals.
Got it. Reduces existing oxides.
And finally, solvent flux, also used during heating. This actively dissolves and removes oxides, washing them away so the filler can bond to clean metal. Also often fluoride-based for base metals.
So protect, reduce, dissolve. A multi-pronged attack on oxides. What makes a good filler metal?
Needs a few things. First, its flow temperature when it gets nice and runny needs to be significantly lower than the melting point, solidus, of the parts being joined. Usually at least 55-60 degrees C lower.
Gives you a safety margin.
Exactly. It needs good wettability. It has to the substrate metal spread out on it easily.
Right.
And good fluidity. It needs to flow readily into the tiny gap between the parts.
Lower melting point, wets well, flows easily. Got it. What are common mistakes here? What goes wrong?
Gap width is a big one. Too wide, the joint is weak, just too much filler. Too narrow, the flux can't get in properly or gets trapped, causing voids.
Okay, the gap matters.
Flame position, if using a torch. You need to use the right part of the reducing zone, usually orangey, to avoid creating oxides. Not the blue oxidizing part, not the yellow unburnt gas part.
Reducing zone, got it.
And just general temperature and time control. Too hot, you damage the main parts. Too cool or too quick, the filler doesn't flow right. Weak bond. It's a skilled technique.
Definitely sounds like it requires skill and attention. Wow, okay. We have covered a ton of ground today, from basic definitions to joining techniques.
We certainly have. I mean, just to recap the big things. Understanding alloy classification, noble content, mechanical types, that's fundamental.
Right.
Knowing those desirable properties, biocompatibility, corrosion resistance, the right thermal behavior, strength, stiffness, explains why certain alloys get picked. For PFMs, it's all about that metal-porcelain bond, the oxides, the thermal match.
Yeah.
For RPDs, you need that mix of rigidity and adjustability, plus biocompatibility and reasonable cost.
Makes sense.
And soldering and brazing, critical skills for putting complex restorations together accurately.
It really is amazing when you stop and think about the sheer amount of material science packed into something like a dental crown or a partial denture, isn't it?
It really is. You look at it and it seems simple, but underneath, wow.
Makes you wonder what's next, you know? With digital dentistry booming, are we seeing new alloys developed? Even better biocompatibility, maybe easier processing?
That's a great thought to end on. Research is always ongoing. New materials, new techniques. It's a constantly evolving field. Maybe the next time you see or hear about a crown or bridge, you'll pause and just appreciate the hidden complexity, the science that makes it possible. It's pretty remarkable engineering happening right there in people's mouths.
Definitely gives you a new perspective.
Yeah.
Well, thank you for walking us through all that. That was a fantastic deep dive into dental alloys. Hopefully everyone listening feels they've got a much better handle on it now.
Hope so. It was fun to discuss.
Thanks for joining us on the deep dive. We'll catch you on the next one.